Welcome to all of you in our next practical of microwave engineering. So students, today we are performing a practical on E-plane T. So in our previous practical we have done the experiment on H-plane T. In our today's practical we are performing practical on E-plane T. So as all of we know that your E-plane T, it is also a 3-port device. So you are observing a diagram of your E-plane T. So port 1 and port 2 are the collinear arm, and E arm, it is nothing but the side arm, which is now nothing but your port number 3. So this E arm, it is connected in E plane, so that's why it is called as E arm, right? In our previous practical we discussed about the H plane T. In that H plane T, whatever the side arm, that is H arm, it is connected in H plane, so we are calling it as a H arm. So before doing a practical setup, let us have a look over the basic working principle of your E arm. So dear students, if we give input to the E arm, if we feed microwave energy to the E arm, this microwave energy gets splitted into your port 1 and port 2, that is nothing but the collinear arms, which is equal in magnitude but opposite in phase. In H plane T we discussed that the energy gets divided equal in magnitude and equal in phase, but in E plane T the energy gets divided as equal in magnitude but opposite in phase, or we can say that there is a 180-degree phase shift between your output voltage at port number 1 and port 2. Now for this particular experiment we want to calculate coupling between collinear arm and E arm. So what is the coupling factor? So that we want to calculate. So for calculating such a kind of coupling, first of all we have to calculate the reference voltage, and that reference voltage V1 is nothing but the voltage before insertion of E plane T. So that's why our first step is to calculate the reference voltage V1, and that V1 is nothing but before the voltage measured before insertion of E plane T, right? So why it is called as T? Because it is just look like a alphabet T in your English. So that's why we are giving a labeling it as a T, T-double-E, right? So the basic experimental setup I have just already connected here. So you are observing here the basic experimental setup before insertion of a E plane T. So dear students, this is nothing but your E plane T you are observing here, right? So this is nothing but your E arm, that is port number 3. This is port number 1, port number 2. These two ports are called as a collinear arms. So if I place this E plane T like this way, then we are observing that this arm, it is in E plane, so it is called as E plane T. So this is your port number 3, this is port 1, this is port 2, right? So port 1 and port 2 are collinear arms. Port 3, it is a side arm, which is also known as E arm, because we have connected this arm in E plane, right? So in our basic procedure, if we want to calculate the reference voltage, first of all connect your klystron power supply to your klystron, right? You are observing a klystron here which is mounted on a klystron mount. Then this klystron mount, it is connected to the isolator. Then isolator, it is connected to the variable attenuator. Variable attenuator connected to your frequency meter, and frequency meter, it is connected to your detector mount. And through this BNC connector we are connecting detector mount or this test bench to the CRO, so that we can capable to observe a square wave on your CRO, right? So initially I have not inserted E plane T in the test bench setup. So this particular experimental setup gives me the value of V1, that is reference voltage, that is before insertion of your E plenty, right? So first of all we will calculate your reference voltage, that is called as V1. Now as per our initial setup, this is your meter select switch. Keep it in on voltage position, beam voltage position. Then put your modulation as AM. So AM modulation I have selected. Then your beam voltage knob, it should be fully anti-clockwise. Then your repeller voltage knob, it should be fully clockwise direction. Keep your frequency and amplitude knob at the center position, right? So through this connector and cable, power supply is applied to your Klystron tube. So during generation of microwave frequency, excessive heat will be generated. So this heat is harmful for your Klystron. So we are using cooling fan here to cool down your Klystron, right? Now the function of isolator is that it provides zero attenuation in the forward direction and maximum attenuation in the reverse direction. Because during this microwave communication, if the source impedance and if the load impedance are not matched with each other, then standing waves are generated within this microwave link, and these standing waves are harmful to your Klystron power supply. So that's why, to avoid the standing waves reaching to the Klystron source, we are using isolator. So isolator just passes the energy in the forward direction, but it blocks reverse energy to go to your Klystron supply. So that's why isolation itself is provided. So variable attenuator, so we are placing this variable attenuator at exactly outside position because of we want a zero attenuation. If we rotate it in downward direction, right, so attenuation gets increases. But for a perfect output, keep your variable attenuator at extreme outside position. So I am just placing this variable attenuator to the extreme outside position. Now rotate your frequency meter at one side. So I have rotated it, then connected your detector mount. So at initial condition you are observing a square wave on the CRO, on a plane straight line on the CRO. So once the microwave frequencies are generated, this straight line itself gets converted into the square wave, right? So this is the basic experimental setup. So we will start our practical. So first of all, I will switch on the Klystron power supply. So at initial condition, the beam voltage should be 200 volt, but here you are observing a 202 volt, which is also a acceptable range. Now our next step is that to increase this beam voltage up to 300 volt. So this voltage is necessary for to generate a response from the Klystron. So with the help of 300 volt, the Klystron will respond properly, and the microwave frequencies will be generated, and that will be propagated through this microwave test bench, and we will get a square wave output. So just by increasing a beam voltage 300 or 300 volt, we have to wait for 1 or 2 minutes so that your Klystron tube will respond properly, right? So meanwhile, for waiting period, just we will take the review. This is your E plane T. Now we are applying input to your E arm and measuring output at these two collinear arms. So we have to check whether this input given to your side arm, that is E arm, itself gets divided into these two arms properly. So whatever the output, it should be equal in magnitude but opposite in phase. So that we have to perform. So we have already waited for 1 minute. Now I will reduce this beam voltage to up to 265 volt. So 266, 67, it is also okay condition, right? Now I will check the beam current. So you are observing here 16 milliampere beam current. So it is also okay. because this current should not exceed more than 30 milliampere. So we are observing 16 milliampere current as a beam current. Now I will just rotate the meter select knob to the repeller voltage. Here you are observing minus 274 repeller voltage. Now I will change the repeller voltage so that a square wave itself generated on the CRO. So dear students, here you are observing a square wave that is generated on the CRO. Yes, so I will just take the reading, just a minute. So it is 1, 2, 3 and 4. So it is 4 multiplied by 0.1. So this is nothing but the reference voltage I am taking. So I am calculating the reference voltage V1 before insertion of E plane T. So V1 is equal to 4 into 0.1. So that is equal to 0.4 volt. So this value we are taking as the reference value for your E plane T coupling factor calculation, right? Now our next procedure is that we are now just disassembling these connections, removing detector mount which is connected to the frequency meter, and after frequency meter I am connecting this E plane T, right? And so I am connecting E arm as an input, and now I am measuring the output at port number 1 or port number 2, one of the port. So it will give me a coupling factor. So just wait for 1 minute. I will just disconnect your detector mount and connect your E plane T to your microwave test bench. So we will wait for 1 minute. Yes, students, so here you are observing that I have connected E plane T just after the frequency meter. So this is the experimental setup for calculation of your coupling between E arm and the collinear arm. So after frequency meter, just after the frequency meter input, it is given to the E arm. Now I am measuring the output at suppose port number 2 and port number 1 it is terminated, right? So you can consider any one of the port as a port 1 or port 2. So if I am taking it as a port 2, this is your port 1, right? So connected your port number 2 to the output through this BNC connector. So you are observing a square wave. Now I have made the same procedure regarding your Keystone power supply connections, adjusting the beam voltage, repeller voltage, as I discussed in the starting of this practical experiment. So let us measure the output voltage. So it is 1, 2 multiplied by 0.1. So it is 0.2 volt. So we are taking this as a voltage, that is V2. So our next aim is that in our previous procedure we already calculated V1, that is voltage before insertion of E plane T. So it is 0.4 volt. Now I am calculating the voltage V2. So it is after insertion of E plane T. So input it is given to the E arm, that is port 3. Now we are taking at the output at port number 2 and terminating your port number 1. So whatever the voltage we observed, so V2 it is 2 multiplied by 0.1 volt, so which is 0.2 volt. So we are observing, we are giving input to the E arm, that is 0.4. So we already discussed that whatever the input given to the ER, it is divided equally in your port 1 and port 2, but it is equal in magnitude but opposite in phase. So if I am giving 0.4 volt as the input volt to the E arm, and if I am observing the output at port number 2, so whatever the reading I have taken, it is zero point 0.2 volt. So at port 2 I am getting 0.2 volt. Now my next step is that I want to calculate the output voltage at port number 1, that is nothing but another collinear arm. So in this experiment, now if the output it is connected to this port, so I am just shuffling the connections. So now I am measuring output at this particular port, and termination, match termination, it should be connected to this port. So just reshuffle these two ports. So take the output at this particular port and terminate the another. So input it is similarly given to your E arm. So we will wait for 1 minute. I will just disconnect this E plenty and the shuffle the connections between your port 1 and port 2. So wait for a 1 minute. Yes. Okay, student. So okay, students, I have just shuffled the connection. Now I have connected output to this particular port and match termination to this particular port. So your port 1, at port number 1 we are taking the output, and at port number 2 it is terminated, and input it is given to the port 3. So whatever the remaining procedure, it is exactly similar regarding your generation of square wave, right? So this is the experimental setup, right? So here you are observing a square wave on the CRO. So we are measuring output voltage at port 1. So in our previous procedure we have taken output at port number 2. So at output at port 2 it is 0.2 volt. Now let us measure what is the output at port number 1. So if we measure the output, so once again I am observing a square wave, so it is 2 multiplied by multiplication factor, it is 0.1 volt. So I am just taking this reading as a V3. So our next aim is to calculate V3 after insertion of E plenty. So input it is given to E arm, that is port number 3. Output I am taking as a port 1. So in your previous procedure, output we have taken at port 2. Now we are taking output at port 1. Now in previous experiment procedure we have terminated port 1. Now we have terminated port 2. So whatever the output it is 2 multiplied by 0.1, which is equal to 0.2 volt. So we are applying input 0.4 volt to the E arm, and we are getting output as a 0.2 volt in the collinear arm. So here we already discussed that we are applying a 0.4 volt as a input. So in our initial procedure we measured the output at port 2, which is 0.2 volt. Now currently we have measured the output at port 1, so which is also a 0.2 volt. So whatever the input given to your E arm itself gets equally divided in magnitude. So 0.4 it is given, 0.2 volt we are observing here, and 0.2 volt also we are observing at another port, right? So these outputs are equal in magnitude but opposite in phase, or vice versa. What we say that if we apply input of equal magnitude to your port number 1 and port number 2, we will get subtractive output at E arm. So it is nothing but the subtractive principle, right? So in H arm we are getting additive output at H arm. In your E plenty we are getting subtractive output at E arm, right? So we are not doing that particular procedure. We have just giving input to E arm and observing the output at port 1 and port 2. So it is equally divided in magnitude that we are observing, but the phase difference it is out of phase, that is 180 degree phase shift, it is available for port 1 and port 2. So if we want to calculate the coupling between port 2 and E arm, the formula it is 20 log of V2 by V1. So V2 it is 0.2 volt, V1 it is 0.4 volt. We can easily calculate coupling factor. Similarly, if we want to calculate a coupling factor between port 1 and E arm, so we have already measured V3. So formula it is 20 log of V3 by V1. So V3 is available, that is 0.2. V1 is available, that is 0.4. We can calculate coupling in dB with the help of this particular formula. So this is all about the E-plane T experiment. Hope all of you understood the concept of E-plane T. In our next practical, we will talk about the EH plane T, that is called as magic T. So meanwhile, we will stop here. So thank you very much.